You ready? If no one has any questions, today I want to talk about how we melt metals before we cast them. We may get a little bit into some of the casting today too. Well, hopefully we will. But one of the things I like to point out is it's not that easy to melt steel. In fact, I always say if it was so easy to melt steel, we didn't need Sir Henry Bessemer in 1856 to teach us how to melt steel and bring us into the steel age. And it really was Bessemer who did that. I mean, we had steel going back thousands of years, but most of it, virtually all of it, was either meteoric iron. You know, someone found a big meteor somewhere and they beat it into swords, typically, or it was solid state diffusion iron, where they essentially took iron ore and put it in a big, basically buried in the sand, kind of like a clam bake, only this was a iron ore bake. And you would basically throw it in with some charcoal and you'd heat it up in an absence of oxygen. And then you would basically do solid state transformation, and the iron oxide in the presence of carbon would turn it into sponge iron. It was a solid state diffusion process. You never melted the steel, and when you're all done, you get this spongy mass of iron, which had all kinds of other impurities in it, and then they would just beat that and forge it. A very inefficient process, but that's how they got swords of 1,000 years ago. It wasn't really until Henry Bessemer taught people how to melt steel. Now, it turns out the Bessemer Converter, all you really have to do, but no one realized this, the problem is that a typical fuel air flame, and the fuel can be, it can be natural gas, it can be wood, it could be charcoal, it could be coke or whatever, is only about 2,000 degrees Fahrenheit, and I'm going to prove that to you in a second. And steel melts at around 2,500 Fahrenheit. Well, obviously you can't melt something at 2,500. A Bessemer converter is just a vessel turned on its side, kind of like this, and typically has an asymmetric spout, and it blows the air in. Well, I should do it a little bit. It blows the air in through a tube, and the metal is down here, which actually starts out as cast iron, which you get out of a blast furnace, and they blow it in, blow air in. Actually, I got this wrong. They don't blow it all the way like that. They blow the air in here. I got it all wrong. I haven't looked at the Bessemer converter for a while. But anyway, they blow the air in here, and well, I guess they're blowing it this way. Anyway, the air coming in here, and the air and the stuff coming out here, this is hot gas off the top, and this is cool air coming in, and the cool air gets preheated in this zone right here by the gas going out. Now there's a lot of mixing in here, but nonetheless, if you do the Bessemer converter properly, you preheat the air. And if you preheat the air to 1,000 degrees and now burn it, okay, or you have the flame temperature, you get enough temperature to get in here and turn the cast iron into steel. Well, I can prove to you fairly simply, as long as the safety office doesn't know what we're doing in the classroom. This is a piece of steel, and I can put it in this is a propane flame. Not doing very well today. Should start to glow red. Yeah, okay. So it's glowing red, and I can hold it there all day long. And that's probably only about 1,600 degrees. Anybody want to feel it? So that's a pure hydrocarbon flame. Okay? It's a pre-mixed flame. It's burning in air. Now, what we actually do today in most steel mills is we use pure oxygen, and you can easily get up to the temperatures. But back in 1856, they didn't have any source of pure oxygen. So they had to come up with the Bessemer converter, which basically was a vessel that when they blew the air in, just like the blacksmith with his forge, he was blowing air on the fire to get it hotter, but if you blew it in the right way, you could basically preheat it with the air coming out, and that's allow them to get temperatures sufficient to melt the steel. Well, today we have lots of different ways to melt metals, and essentially you could almost, I haven't categorized it this way, look at radiation and conduction in a reverberatory furnace, and we're going to see that basically happens to be a version of the open hearth. A cupola, which I mentioned before, in the great leap forward in China in the 1960s, they started building cupolas at every little commune in China, and so they could all make little cast iron parts. The blast furnace is just a big version of a cupola. You use electric energy. So this is a blast of hot gas. This is hot gas coming in over the top of a molten bath. Electric arc, you're using electric energy. Induction, you're using electric energy, but you're using the electromagnetic fields rather than current. Vacuum induction is just a variation on that, and we'll talk about why. Plasma, which is again electricity, but turning it into an arc plasma. Crucible, we don't use crucibles for melting steel. Crucible melting is typically for coppers or aluminums or other things that melt at lower temperatures. Electroslag, again, we'll talk about each one of these. Electricity, vacuum arc is electricity. Skull melting can be electron beams, arcs, induction. So in general, we're using radiation, conduction, or electric energy in most cases to do the melting, okay? But there's lots of variations on that, and I want to talk about some of the industries, but what's the big industry? The big industry for metals is steel, so we're going to talk some about steel. Okay, now with this, we have to worry about, after we melt the metal, we've got to give it some, oops, turned it off. What did I do? What happened to it? Off, no signal. Pardon me? Did I unplug something? Did I? Maybe I turned this off. Oh. No. Well. Maybe I hit a button and I didn't. It's like it's not getting a signal. Off, no signal. Oh, that's interesting. Oh. Off, no signal. It was just there. On the Elmo. Lamp. Image rotation, white balance spots. Yep. Hey. I guess I turned the power off on the Elmo. Okay. So once you get your metal by some melting technique, you've now got to solidify it, and so you're going to have to extract the heat of fusion. We'll get to that. You're going to try to impart some geometry and structure. Initially, when we're just making steel, we're just trying to make plates or sheets or bars or something like that, just long round slender objects, I guess I should call them. And we have to worry about a number of things. We'll talk about some of those things as we go on. But to get into, go back to some of the steel stuff, we start off with this iron ore, limestone, and coal, and we put it into a blast furnace. A blast furnace is nothing more than a great big cupola, okay? And we're going to have these preheaters over here. That's what these things are. And then eventually we're going to either make an electric furnace, open hearth, or a basic oxygen. And I want to talk about that. I don't think I talked about the ratio of those and time and stuff last time. Pretty sure I didn't. Anyway. But let's just talk about a cupola first. A cupola, the simplest version of it, is something like this, where we basically just have a big tall shaft. We have a charging door at the top, and we pour our solid materials in. We have, they call it a refractory bed here, but don't worry about that right now. But basically, the stuff just keeps falling down here, and you put your fuel in here with the air, and you just blast it in there. And so heat things up, and at the bottom, your impurities will melt and form a glass. We call it a slag. You have your metal, and they basically just put a little clay plug in there, okay, a little dirt plug, and every now and then, every 6 hours, every 12 hours, they knock out that plug, and the metal comes running out. And after the metal comes running out, the slag comes running out. And typically, you'll take the slag off one side, you'll take the metal off the other side of the furnace, and you just keep on. This is a continuous feed furnace up here, okay? And so this is how the Chinese, they built thousands of these all around China. This thing's not working either. Nothing's working today. Go away for a week and anyway. So they built thousands of these. Well, the steel blast furnace is basically the same thing, just on a much, much larger scale. And so this thing can be 30 stories tall, so far as that goes. And you put your charge in here, and it starts out relatively low temperature, and it just gets hotter and hotter as you get to the bottom. They call the tap hole here the slag hole. Tap hole is a little lower than the slag hole, because this is where the molten iron is. Remember, we started out with coke, which was coal that had burned off the volatiles, and so we had carbon in here. And what we end up at the bottom here is we've reduced the iron oxide with the carbon, and so you get a lot of carbon monoxide coming off this. And that comes through here, and it heats up the brickwork in one of these. Actually, the way they're showing it here, it's heating up this brickwork, and that gas goes off to run the rest of the steel mill, because it's carbon monoxide. It's a fuel gas. Might poison everybody if they breathe it, but it's a fuel gas. You can burn it to heat up things in furnaces before you're going to forge things or roll them or whatever. The other air coming in is preheated, because the thing runs more efficiently that way. And basically, these are just two big heat exchangers. One of them to preheat the brickwork, and the other one to preheat the air and cool down the brickwork. And they just shift it over like every 12 hours. These are huge things. It takes 12 hours to heat them up. And that's actually a large part of the expense of the blast furnace, is just these big brickwork lattice things, which are basically heat exchangers. Okay, so this is basically just a big cupola. The slag comes off from this side. You take 50 tons of slag off here. You take 300 tons of cast iron off here. This is carbon saturated iron. Melts at about 1450 or 1600 degrees Fahrenheit. Yep.
Is there anything you can do with that slag waste product? Or?
Not a lot. You can use it you can break it up into gravel, basically, and put it with asphalt and pave roads. Blast furnace slag is not as bad as steel making slag, and you can spin it into slag wool like insulation. Okay, like it's not Owens Corning pink fiberglass; it's sort of a black stuff, but it's a problem. Okay, blast furnace slag is not as bad as steel making slag. But one of the problems in the world is we produce a couple of 100 million tons a year of slag, which goes into landfills by and large. Okay? Yeah.
Reefs.
You can make reefs. Well, not with steel making slag. There's a lot of impurities in there that are that the environmentalists don't like, okay? But for a blast furnace slag, it's fairly simple. It's just kind of limestone and silica and stuff, and so it's not too bad. You could make reefs, but how many reefs do you want to make, you know? You can't fill in Boston Harbor anymore, okay? So all this slag is still a problem. But they've done all, you know, everybody says, oh, we're gonna whether it's old rubber tires or whether it's blast furnace slag, whatever it is, they say, well, let's mix it in with asphalt and pave the roads. Well, we don't have that many roads to pave, okay, for all the junk that we want to put in there, okay? So these things actually do create something of a problem. But they found, believe me, there's a big enough problem. People have been fairly creative about what they try to do with them, and probably about 50% of it doesn't go into landfills, goes into making insulation or products or something else. But when you make this much of something, it takes a lot of whatever it is to make all that. So here's a little bigger version. You've got big blowing fans. I think I showed you this one before. This is a man sitting next to this. So you got huge blowing fans. It's just a cupola, but they call it a blast furnace just because it came up through kind of a different genealogy. Now I thought I didn't show you the open hearth before. The open hearth is basically, here's your bath here, and it's a reverberatory furnace. You basically have this big brick checkerboard to heat up the incoming air, and on the other side it says similar chambers on the other side, which would be back over here. So it comes in, goes across the top, goes out, heats up the checkerboard there, and every half day or day they switch the flow, and you have your steel ladles. You tap it every now and then. Typically, to tap these things, they put a charge in there, and you don't want to lose 300 tons of steel, so you put a pretty good charge in there, and they actually use an explosive charge to open the tap hole. Okay, just stick some explosive in there and blow it apart. So this is large scale stuff. Okay. So anyway, this is a very inefficient process because just radiation and conduction of hot gases are going across the top. What are we doing in these furnaces? All the carbon that got saturated in the cast iron in the blast furnace, we got to get that carbon out. And we have to go from 3 or 4% carbon in the cast iron to about 10 times less to make steel. You got to get the carbon out. And you got to oxidize it in the air without oxidizing the iron too. If you oxidize the iron, you're right back to the ore, and that doesn't do you any good. So it's a balance of how much air you put in there, how much oxygen to burn off the carbon, which burns off preferentially to the iron. Okay. Now the basic oxygen furnace is just a quick version of the same thing, except it's a smaller vessel. Here are your slag pots, and you have an oxygen lance, you have an oxygen plant next to this. We talked about some of this stuff before. I'm being a little bit redundant, and we'll talk about that. The electric arc furnace, which is the third way to do it, is basically 3 carbon electrodes about 36 to 42 inches in diameter, and you're going to have 300 or 400 volts at 50,000 amps, about 150 megawatts of power. And in this, you can charge all 100% scrap because the arcs can melt everything. In the basic oxygen furnace and the open hearth, you have to start with about 70% cast iron because you have to have liquid. If you throw some solid scrap in, you can, but no more than about 30%, so you don't freeze your bath. If you don't start with a liquid bath, you won't get the chemical kinetics to be able to burn off the carbon. If it's solid, the oxygen is just going to burn off the top surface layer. You need the convection in the liquid to bring fresh carbon to the surface so you can oxidize away the carbon. Okay, so you have to start with virgin iron ore. And I don't think, did I show you this plot before? I did. Okay, so I already showed you this plot, how the basic open hearth died, the BOP. So sorry about that. Okay. I I couldn't remember where I went. Oh, actually, I probably got to this and told you how the BOP can make things in 45 minutes. Well, if you got 300 tons of steel in the pot, if the cast iron's worth a couple of $100s a ton, maybe $300 a ton today, and when you make it into steel, it's now worth $400 or $450 a ton, you're talking about a value added of $150 a ton to take the cast iron and to make it into molten steel. And if you got 300 tons in the furnace, 300 times 150 is that $450,000? Is that right? Did I work that out right? Yeah, 450,000. 300 times 150? Huh? 600? Wait. 450,000. So $450,000 an hour that's coming through this BOP shop worth of value added. Okay, but the value of the product, you've already got $300 worth of per ton of cast iron. So the actual value of the product, if you screw it up and if you had to throw it away, you don't have to throw it away. It can always be reprocessed. But if you had to throw it away, you've got over $1 million an hour worth of product coming through this plant. So it's a substantial investment for these things. Anyway, 45? Is it 40? 45,000. Okay, so 100,000 an hour. Okay, 45,000 an hour of value added and about 120,000 of product going through there. Anyway, those are the three basic types. And in the old days, back in the 1960s and before, we basically would cast it into an ingot. And there's lots of different types of ingots. You have a big cast iron mold, and this is what the steel would be cast into, these different types of shapes. Depending on the chemistry of the steel, how much gas is in it, you might get the steel actually as it cools down, it will give off the gas, it may actually start to boil. And you'll get what they call a carbon boil. It's actually carbon monoxide boil, but they call it a carbon boil. And so you can essentially fill up the whole vessel. If you have done something to get rid of the oxygen in there, like adding aluminum or silicon or manganese, you'll end up with no carbon monoxide boil, and you'll get solidification shrinkage. You're going to have to cut off the top third of that ingot. Okay? So to make really heavy plates above about 4 or 5 inches thick, we still have to use ingot technology. But today, 97% of the steel in the world is made by continuous casting. Yep. Oh, all the variations here? This is what they call a semi-killed steel, and it's not a very good structure. The other variations here, they may have what they call hot tops on here to try to melt some of the, keep the heat on the top. They basically just make a kind of like a thermite reaction, and they put it on the top and they try to get the hot top smaller because you're going to throw away 1/3. I mean, if you want, I can dig up the thing and go back to the making, shaping, treating of steel, but there's lots of variations. It turns out the old sheet steels, they used to like to make this. It was called a rim steel, and this is different amounts of rimming action, the boiling, carbon boil. But you get porosity in your steel, but if you're going to roll it into sheet, it's all going to get welded together anyway. If you're going to make good plate, and you're not going to roll it as much, you got to go with a killed steel. If you get rid of the oxygen before you pour it, it's called a killed steel. This is a semi-killed steel. These are unkilled steels, or we call rimmed steels, and these have carbon boils. These are for sheet material. This is for plate material. Does that answer your question? So those are things we had to worry about. In the old days, rim steel gave excellent surface quality, whereas plate steels, you end up with inclusions and other things on the furnace, on the surface. Now, starting in the steel industry in the 1960s, we had this other thing that improved productivity. We haven't done much with the blast furnace for the last 400 years in terms of improving productivity. and we've done something, but it's all sort of incremental. But we went from the open hearth after 100 years, we went to the BOP, and we got this tremendous increase in productivity. About the same time that we did that, we went from ingot casting, which was essentially 100% of all steel, to now it's only 3% of all steel in between 1960 and 1995. And what we did is we went to continuous casting. And the first continuous casting, you come out of your melting furnace, your BOP, or your open hearth or whatever, and you pour it into a ladle. The ladle would go into something, a stationary holding vessel, essentially called a tundish, and then you pour it into a mold. Well, these are huge water-cooled copper molds that vibrate back and forth. I mean, they may only weigh 50 tons or so, but they're vibrating them. And as the steel comes in here, the water-cooled copper extracts the heat of fusion. Remember I said you had to take out the heat of fusion to cast it? And you come down here, the stuff is still hot, and initially it was just a big, tall, vertical furnace, so this could be 30 stories tall again, and you would cut it off. Now you're going to see in a second, they actually got to the point where they went from vertical to essentially they curved the steel. It's still hot here, so you have great big rollers. Now the interesting thing here is you're going to have 500 tons of steel in the tundish, and if you don't extract the heat well enough, or when you start curving this, here's a curved one, the curve going the opposite direction, and this is probably about $1 billion facility right now to build one of these, maybe a couple of billion. So here's your tundish, here's your your ladles, and you keep on bringing them over, and you may run a continuous caster continuously for a month or two. You may have to shut it down every now and then to replace refractories and wear and whatnot, but you just run it 24 hours a day, okay? You can't afford to shut this thing down. But you have all these rollers. If you have a breakout, okay, breakout means all of a sudden you no longer have a solid shell and the molten steel just falls on the floor. Well, that shuts down your continuous caster for about a week or two to clean that up. And so if you're talking $100,000 an hour, we're talking some real money. People don't like to have breakouts. And nowadays we don't have as many breakouts. But back in the 60s and 70s and stuff, you were lucky if you only had one breakout a year. And so it took some time to get to the point where they could control things well enough. Here's a person down here. Now, when you come off here, and I'll show you some pictures a little bit later, you basically can cut this stuff, even though it's a big, thick steel. We can melt something 10 inches thick. Some places go as much as 12 inches thick. They can't go much thicker because you've got to extract the heat of fusion. And the thicker it is, the longer it takes to suck the heat out of the inside. And it goes as the square of time, okay? The thermal, whatever your heat flow equation is that you want to use, they always have the form of the distance that heat travels is proportional to the square root of the thermal diffusivity times time. So the thickness, x, goes as the square root of time. Or if you want, x squared goes as time, okay? This is a material property, thermal diffusivity of the steel. And so if you go up from 10 inches to 14 inches, you got 50% greater time, you got to have 50% greater height and bigger molds and everything else. So about the thickest we can go is something on the order of 10 to 12 inches. You have to you'll have some defects in here, you're going to have to roll it to get rid of some of those defects. So generally the thickest plate we would bake by this is 2 to 4 inches thick, okay? Anything thicker than that, we still have to go back to the old-fashioned ingot casting. And ingot cast molds can be 30, 40 inches thick, okay? Typically, the old ingot casting lines, you have 300 tons of steel, you might cast 15 ingots. So it's about 20 tons an ingot. And if you're in the steel mill and someone is not careful and they fall into the ingot, they bury one ingot from the heat, okay? This is the way they did it, okay? So the graveyard, they just bury one ingot. When I was at Bethlehem Steel, there was one guy who had just retired, and I guess he couldn't really handle retirement. So he came back to the plant one day and he dived into the bath of molten steel in the BOF. They were sitting there waiting to get chemistries back, and they saw a poof on the TV screen, and they looked in and they could see this body spread eagled on the molten bath of steel floating on it. You float really well. I mean, the density of steel is much heavier. But he had committed suicide by diving in there. So what do? They'll bury one ingot when they tap the steel. Okay. Steel mills are hazardous places. There are people who would be working there on the hot tops on the ingot casting floor, and they would, every now and then someone might trip and fall in or something. It's not, it's actually a fairly quick way to go. But the old steel mills were just places to just maim people. My second child was born in Bethlehem, Pennsylvania, and wonderful hospital for a town that size, because it was just a couple hundred yards down from the steel mill, and they had, they'd take maimed steel workers who were, in the old days, like the 1930s and 1940s, when you're rolling bar, it'd be coming through at a piece of hot steel, a mile long, coming through at 40 miles an hour, and the guy was supposed to grab it with tongs and put it into the next stand, and if anything happened, they called it a cobble, and the thing curved when it came out, it might just cut his arm off. But it cauterizes the wound at the same time. It's hot. But it just cut through human flesh like a knife through hot butter, or a hot knife through butter. Well, nowadays you walk through a steel mill and you have to have a reason to be down there on the floor. They basically have the people in protected pulpits with armored glass and everything else. So it's not anywhere near as bad as it used to be. But just like we now have all kinds of people in Cambodia with missing legs because of landmines, we used to do that in steel mills 70, 80 years ago. We had people with missing limbs all over the steel mills because it's just a hazardous place to be. And it's not like that anymore, but there's a reason why unions have a lot of power, okay? If you look at what people had to go through in the old days. But anyway, this continuous caster, a continuous caster could produce 4 or 5 million tons of steel a year out of one caster. Now, after casting the steel, you really have to start worrying about getting rid of some of these other things. I mentioned, well, I didn't really mention it too much, but if we look back at some of these other requirements of what you've got to get out of there, you've got to extract the heat of fusion. And by the way, one of those 40-inch ingots, it may take 2 or 3 days to solidify. So once you cast those 40-inch ingots that you're going to forge some big thing from, you got to let them sit there for 2 or 3 days, and you can't jostle them. You can't pull them away in the railroad car, because if you vibrate them as they're solidifying, you're going to introduce defects. So when you had ingot casting, and we still do have ingot casting, when you're making really large parts, like a big shaft for a propeller or something, that costs a lot more money, because they have to cast it, and that part of the plant, nothing happens for 2 or 3 days while it's solidifying. So, and that's just basic heat flow. You can't speed it up. Nature gives it to you. You got to extract the heat of fusion. You can have shrinkage, which can give you this porosity at the top we talked about. You can have gases, which can create the boil. You can have liquids, which end up as inclusions. You can have segregation. It's an alloy. It's got carbon, manganese, silicon, and other alloying elements, and they may not be homogeneously distributed. And we're going to talk about some of those issues, but one of the issues is getting rid of the gas or the liquids that you don't want, the impurities that are still in the steel. So one of the things you can do is you might pour from your electric furnace into this holding vessel called a tundish. You might add alloying elements at that point in the ladle. You may have this thing with an exhaust connection, and you're going to pull a vacuum on this. If you pull a vacuum on this, you're going to try to pull out all those gas, the gas that's dissolved in the steel. Just like the rim steel will give you a carbon monoxide boil if you don't want that. or if you have other impurities, and this is not just steel, hydrogen and aluminum, okay? Just the moisture in the air will introduce hydrogen into the aluminum. If you solidify that, you're going to end up with Swiss cheese. It can be full of holes. So you've got to do something to process the liquid. So this is just a schematic of tap ladle, teaming ladle, big vacuum chamber, and exhaust lines, vacuum tank, and you're basically just going to suck all those gas impurities out of there. This is vacuum degassed steel. Costs about $20, $30 a ton more for vacuum degassing, but makes it very pure in terms of the gas impurities. So another thing is, might as well blow this up, is vacuum oxygen decarburization. Now this initially started, actually this was invented in the basement of Building 8 here. And well, not all, but about 98% of all stainless steel in the world is made this way now. Stainless steel is an alloy of iron and chrome, and a lot of it is iron, chrome, and nickel. But you want low carbon, or I'll call it ultra low carbon. And ultra low carbon means 300 parts per million or less. In the old days, with the electric arc furnace, in the old days before the 1960s, people had to heat it up in an electric arc furnace. They had to put a slag on. They had to take that slag off, put a cleaner slag on. They had to keep it in the furnace for hours to burn off the last amount of carbon. But because of some research, basic research that was done here in the basement of Building 8, they were looking at what happens when you bubbled argon through the bottom of the steel bath. And what happens, instead of having a bubble in your molten bath of steel of 1 atmosphere of carbon monoxide, you can get it down, if most of your gas is argon, the partial pressure can be 1/100th of an atmosphere of carbon monoxide. If you just look at the thermodynamic equilibrium, you can drive your carbon down very low. The simple reaction, for those of you that are chemists, is carbon, and we put an underline for dissolved in the steel, plus oxygen dissolved in the steel, goes to carbon monoxide gas, and the equilibrium constant of that is the pressure of CO gas divided by the activity of the carbon times the activity of the oxygen. You want to drive this down as low towards 0 as you can. You actually want to drive both of these down towards 0, but in order to do that, you have to have a low CO pressure. Well, if you're just getting a carbon monoxide boil in the steel bath, it's 100% CO2 or CO, and that's 1 atmosphere. So 1 over the product of these, you can't get the carbon down unless you get your oxygen up. Okay, well, if you drop this by a factor of 100, by having 99% argon and 1% CO, you can get this down much, much lower. So today, almost all of the superalloys, the nickel-based alloys for turbine engines, even carbon steels today for high-quality parts, aircraft landing gears and things like that, go through argon oxygen decarburization. You basically have a vacuum chamber of the molten steel and oxygen lance that you can blow some oxygen in to get the carbon down, and you also will bubble argon through the bottom. Okay, so this is vacuum oxygen decarburization, but if we look at some other things here, I should have, oops. Here's the picture of argon oxygen decarburization. So you have argon blown in here and just a big vessel to do that, and here's actually a better picture of, you got auxiliary oxygen to get the carbon down. You blow the oxygen. Nowadays we actually first blow with nitrogen. You can't blow with all nitrogen because then your nitrogen in your steel will go too high and that can create problems. But you start off with nitrogen, get most of the oxygen and carbon out, and then you finish off with argon. Argon's expensive, but so is stainless steel. And this is a plot showing the carbon content versus the chromium content. Electric furnace practice was down like this to get down to, this would be 200 parts per million. You really want to get below 300 parts per million of carbon. The AOD practice goes this way at much higher chromium content. The old process, you had to get it down low and then add your chromium as an expensive type of chromium. Nowadays we can use cheap chromium. Basically this process has reduced the cost of stainless steel in the world by about a factor of 2 per ton since the 1960s. If you go back to, this is chromium content versus temperature. Temperature in the furnace, you actually heat up your steel to higher temperatures because you're burning off carbon. You're adding heat when you blow the oxygen in there. The chromium goes down a little bit, you add a little bit more, but the carbon comes way down to these levels that you need to have good weldability, good corrosion resistance in your stainless steel. So, something that was initially developed at MIT, but it also brings up an interesting point. Someone did a study in the early 1990s of how many innovations in the steel industry were brought about by the steel industry. And essentially it was 0. Things like argon oxygen decarburization was done by a company that wanted to sell oxygen to the steel industry, and argon. It was the liquid, it was the gas companies saw this as a way to sell more gas to the steel companies. Continuous casting was really brought in by companies who wanted to sell machinery to do the casting. The basic oxygen furnace, that was really brought in by companies that wanted to sell the gas, pure oxygen, as opposed to no one can buy it, no one can sell air. It's pretty free, okay? But it was interesting because out of dozens of improvements in the steel industry in the world, none of them over the last 75 years were done by the steel industry itself. And that's because we had this fantastic management in the 1950s and 60s in the US steel industry. They had bombed out all their competition. They were making money hand over fist, and they thought they were the greatest managers in the world. Well, actually, they were probably some of the worst managers in the world, but no one could prove them wrong because they had no competition, okay? And so it's sort of, you know, you can say, well, it's too bad that Bethlehem Steel went away and all these other steel companies went away. Well, yeah, it's unfortunate those workers who were having their arms cut off lost their jobs, but to think that that management lost their jobs, that's actually a positive thing, okay? I worked at the steel company for 13 months before I said, where do I want to be 5 years from now? And the clear answer was not here, okay? And so by 20 months I was gone. But it was just, I mean, today I would use the word corrupt, but they had 3 or 4 Learjets parked at the Allentown airport, and their primary function was to fly the executives to Florida on the weekends in the winter so they could play golf, okay? Now, the only other organization I've ever seen doing similar types of things was the US Air Force Reserves, where they had to get their flight hours in, and they would fly cases of Cokes over to Tokyo, Coca-Cola, over to Tokyo on C-5As so the pilots could get their time in. And so they could go to the electronic shops in Tokyo and buy stereos and stuff cheap, okay? But that was because, you know, it wasn't the same type of corruption. They weren't making any money. They could just buy cheap stereos for their friends and stuff. And I could buy Coca-Cola in Tokyo cheaper than I could buy it in the United States per case, okay? Flown over, air freight, courtesy of the C-5A and the US Air Force Reserves, okay? But anyway, it's an interesting system of economics in the world sometimes. Other types of melting. So we have cupolas and blast furnaces to make cast iron. We have electric arcs, that's the electric arc furnace. We have induction melting. Well, induction melting is nothing more than a big pot. In fact, you haven't taken them to the foundry downstairs, have you?
Nope, not yet.
But there's two induction melters down there that are what, about 200-pound furnaces? Something?
Yeah, full charge.
Okay, if you put a full charge. They're a couple of 100 pounds, but you can get induction melters that are 100 tons. And there's one guy, graduate of MIT, who basically bought Inductotherm and Lapel, and there were only 2 or 3 big induction melting furnace companies in the world. He ended up acquiring them all, getting sort of a monopoly on it. His name was Henry Rowan, and he kind of wanted to have a university named after him, but he didn't have enough money to convince MIT to change their name. He went to New Jersey Institute of Technology, and they wouldn't do it for 100 million, or 200 million. So he went to another school in New Jersey, because he was out of somewhere just north of Philly. And he convinced this other school, I can't remember what its name was before, but it's now Rowan Institute of Technology, okay, because he gave him a couple of $100 million. So anyway, induction melting is basically just a big water-cooled copper coil. And it can be, I mean, I used to have one in the lab that was not, much bigger than your fist, but it can go up to about 100 tons. Big, heavy AC power leads. The frequency, I mean, the little ones, because we have things called a magnetic skin effect. This is a cross section. These are the copper coils, big crucible. Basically an AC induction. And if you're talking a 100-ton vessel, this might be in the 60 hertz frequency range. But if you're talking the little ones in the lab that can heat up foils and things like that, you might be talking a megahertz frequency. So there's lots of different induction units, but you're using AC induction to generate eddy currents of electricity in the molten bath, or the steel can be start out as solid steel, but you essentially electrically resistive heat by coupling to the steel with induction, okay, magnetic induction, AC effects. Just like an electric motor, an induction motor, you're expanding and collapsing the field and generating an induced current in the metal. And so you can melt all kinds of things, nickel-based alloys, not just steels. In fact, relatively small amounts of steel are melted by induction melting. Vacuum induction is, again, just a more expensive furnace if you want to make higher quality and get the gases out, the impurity gases that will dissolve in the molten metal, then you run it in a vacuum furnace. And I don't know that we have, I think Ron Ballinger's got the old vacuum induction melter over across the way. But we used to have a big vacuum induction melter. Vacuum induction is typically the way that you melt things like turbine blade alloys and things like that. Nickel-based alloys, things that are going to go into products that are worth thousands of dollars a pound, like a jet engine and stuff. In a vacuum, very high quality melting, very pure and nice and clean with the induction heating. Other processes, there's what they call consumable electrode melting, which is just a big single arc furnace where you actually cast a steel electrode, and then you have a water-cooled copper ingot mold, so water out, and you just run an electric arc and melt this just like a great big welding electrode, just depositing metal into a crucible. Expensive, but if you do it with a vacuum, you can get rid of a lot of inclusions and other things. So vacuum arc remelted. This material would be Vim var, okay? Typically for a turbine blade, the vacuum induction melted, and typically for the best materials it has to be all virgin material. Virgin nickel, virgin chrome, virgin molybdenum, no scrap. because scrap will have impurities and oxides on the surface and stuff that'll get into your material. If you're talking about something, one of these turbine blades will go for about $6,000 when it's all done, each, okay? So you're not gonna skimp on the incoming materials. You're gonna do vacuum induction melting and vacuum arc remelting. And it might be double vacuum arc remelted, okay? So if I have a critical shaft, or let's say a landing gear on an airplane, VIMVAR. In fact, it'll probably be double vacuum induction melted, maybe triple. Each time you melt it in the vacuum, you're burning off some more of these inclusions and getting rid of some of the gases and getting down to a very, very pure high tonnage material. Now another process, which is not used so much, certainly in this country, but was used a lot in the former Soviet Union for political reasons, well, not just political. They would cast the steel and they would remelt it in electroslag melting, where you have a molten glass, which is a slag, and just run a bunch of current through here, and the resistive heating in the slag causes the electrode to melt off, and you cast an ingot underneath. You have water-cooled copper mold, and you just drop the bottom of the furnace, okay? It starts to solidify on the bottom, and then you just lower it, and you can make big long ingot. Now, the Soviets, I remember going over, the only time I was ever in Russia, in the Ukraine, was back in 1980, and I went with Julian Sekeli, who was a professor here, who had been a student in Hungary, and left. Did I tell you about Julian? He left Hungary in '56. And I said, well, did you have a gun in your hand? He was a college student at the time. I said, did you have a gun in your hand? He said, well, yeah. Okay. I said, how'd you get out of Hungary? He says, I just took the train to the Austrian border and walked across. But he did have a gun in his hand in the 56 revolt in Hungary. But anyway, Julian was a steel expert on how to make steel. So when we were over there, the Soviets are very proud that of half of the steel they produced was electroslag remelted. And at the time, we would only do this because it's an extra process. It costs you extra $100 a ton to improve the quality. And Julian says, yeah, but that was because the stuff they made the first time around was such a bad quality, they had to electroslag remelt it to get it up to the kind of quality we would get out of our BOP. Or basic oxygen furnace, which was probably true. Their stuff was just junk. And so they had to do electroslag remelting to get rid of all the big inclusions the size of your fist and stuff. Can you imagine a piece of steel that you're going to use for a ship plate or something that has got an inclusion as thick as the plate? I mean, it just pops right through and you got a hole in your plate. Well, that's what the Soviets produced out of their steel mill. And so they had to do electroslag remelting that would remelt it, melt these inclusions, and make a better ingot, okay? There's actually a political reason why they were so interested in electroslag. In Kiev, there was a place called the Paton Institute, Paton, P-A-T-O-N. It's still there. And during World War II, there was a Dr. Paton at the Paton Institute basically was looking at electroslag welding, and he developed this for welding of armor plate. And he was very proficient at getting the Soviet tanks repaired and back to the front to fight Hitler, okay? And so he was, after the war, he was a hero of the Soviet Union, and Stalin decorated him and everything. He was in charge of all the scientific money that went into the Ukraine. And all the scientific money that went into the Ukraine was about 25% of everything the Soviets did. He had his own institute, which should have been 500 people, but because he controlled all the money, it was about 5,000 people. And so he had grown up doing electroslag welding, and so they did all kinds of electroslag processing, and he convinced all the Soviet officials that this was the savior for their steel industry, and it probably was, because they couldn't make decent steel to begin with, okay? But you read things about how wonderful the Soviet steel technology was because they did all this electroslag remelting. It was only because the first part of the process was junk. Okay, so why don't we take a break come back here at about 8:35, and we go on and show that I'm not the only person that believes iron is important. Rudyard Kipling put this together. He said, "Gold is for the mistress, silver for the maid, copper for the craftsman cunning at his trade, goods to the baron sitting in his hall, but iron, cold iron, is master of them all." Steel has properties that are vastly superior. Actually, I should have left that as I had it. To many, many other things. To show you something about the steel industry and what happened because of the switching over from the basic open hearth to the basic oxygen process, and because of continuous casting, you had a tremendous increase in productivity. If you looked at the decade of the 1980s, the United States used about 100 million tons of steel. It turns out there's about 76 million they produced that they sold, and another 25 million they imported. Okay, and except for the recession in '82, this is basically fairly constant across here, believe it or not. It started out the decade at 100 million tons and it ended up at 100 million tons. The employment, on the other hand, dropped by a factor of 2 from a little over 500,000 to a little over a 250,000. So what happens if half the people produce twice the same amount of material? That means in 10 years, the productivity, or tons per person, went up by a factor of 2. Okay? Well, this was the same decade where everybody thought the steel industry was dying. And in fact, it wasn't dying, it was reinventing itself by going to BOP and continuous casting and other things. It also switched to a lot of production coming out of what we call mini mills. And this is a picture of a continuous casting line. It actually was curved up here, behind here. They basically, when the steel is hot like this, if you want to cut it as it's coming down continuously, you basically just take an oxygen jet. You don't have to do anything else. You just blow pure oxygen on it, and it does oxyacetylene cutting right through it. Any thickness you want, 10 inches, 12 inches. I've seen people cut 3-foot thick steel with a solid oxygen jet, okay? As long as it's hot. And when you get to, in another couple of lectures, you'll get to flame cutting and stuff, and I'll explain how that works on your videos. This happens to be one where they're not just doing a big flat 10-inch thick plate. This was a steel company in Midlothian, Texas, run by Gordon Forward, a graduate of this department. But they actually were getting to net shape casting, so they were making I-beams, and they were casting something that was almost a final I-beam product. It took them a while to get there. Here's a slide of one of their earlier products where they had, instead of a simple rectangle, they actually started casting something that was a partial dog bone shape, but eventually they got to the one I showed you before. And they cut their rolling costs down by about 2/3. I mean, if you've got near net shape, you can roll much faster and more productive. And so you got other follow-ons in productivity. Okay, you started out with continuous casting, and then you went to other casting technologies. But for some things, like big shafts and things, you can't do continuous casting. You have to do ingot casting. This illustration just shows them stripping the cast iron mold away from the ingots after they've been solidifying for a few days. And they're typically corrugated on the surface because you don't want them sticking to the mold. You want, as the steel shrinks, you want it to pull away so that you can strip it off. It's sort of a pain when you can't strip it off. And there's a big hydraulic ram here trying to push the thing down if it does tend to stick. But what I wanted to go through now, here, I guess it's over here, is do a little case study since you guys are in the Navy. Now this one I do on one of the other videos, so you can fast forward, but this is in the revised way that I'm putting this together, this course. This is a good place to talk about this particular problem. So this is, anybody know what surveying is in shipbuilding? You don't?
You're checking the status of the production of a ship.
Right. So you got the American Bureau of Shipping, you got Norska Veritas, you got Bureau Veritas. So if you're British Petroleum, actually in the Navy you have soup ship, okay? You're basically, soup ship is a surveying, in the commercial business you would be a surveyor. So if I'm BP and I'm building a $2 billion oil rig to go drill in the Gulf of Mexico or the North Sea or wherever, I want to make sure that that steel company does it right, or that shipyard does it right. And so I will hire the American Bureau of Shipping, and they will send their surveyors in, and they will live full-time at the shipyard just like a guy at Soup Ship does, and they'll walk around checking processes, checking quality control records, doing all those types of things that many of you are familiar with, okay? Also, if you have a failure, Lloyd's of London or somebody will send in some surveyors to say, why did we have this failure? So this is a case study of a failure that occurred in October 1980. And this is the ABS report. Certified, the undersigned surveyor did at the request of the owner's representative. They use sort of old English type of language format because it's going to Lloyd's of London basically. Attend the SS LNG Libra of Wilmington, Delaware. What's this, 79? It's about 125,000 gross tons, I thought. I can't make out what that means. Anyway, as she lay off Davao City in the Philippines, and basically she had lost power, fully loaded with LNG, going from Indonesia to somewhere in Japan, and she just stopped dead in the water. The Libra had been built right down here in Quincy Shipyard, which used to be a Bethlehem Steel shipyard back in the days when I worked for Bethlehem Steel. It's now a auto parking lot, okay, and the big crane and stuff. But anyway, these were LNG's vessels that were built in the 1970s. In fact, I worked on a project to develop a new steel skirt. And they had these big aluminum spheres. If you've ever seen these LNG vessels, these are like 5 spheres the size of the vessel. Each one of them would carry, what, 25,000 or 20, I can't remember. I thought it was 125,000 ton vessels, but they were huge. And they made these huge aluminum spheres that were, at the equator, they were like 12-inch thick aluminum, okay? And they carried the liquid natural gas, and those spheres had to sit on a cylinder, and I was working on the steel for the cylinder. But anyway, by 1980, one of them had a tail shaft failure, and in fact, the next part of the report, this is a little 2-page report when he went to the Philippines. This was an out-of-the-way area in the Philippines, because when this happened, as you may realize, the LNG vessel is all cold liquid, and it will slowly heat up. Now it may take a month to heat up, but it's just basically you're boiling off or you're boiling off gas, natural gas. And if you don't have power and a storm came along, you could have a big fireball. Now such big fireballs have happened. Has anybody ever heard of any with liquefied natural gas? In the late 40s, if you look up LNG explosions, you'll see that they wiped out a fair-sized amount of Cleveland, Ohio, when a tank of LNG blew up in the late 40s. There's another one that you will not find if you Google it. They blew up the entire harbor in Qatar, in the Persian Gulf, when a tank of LNG exploded about the same time, about 30 years ago. That one has been sort of quieted down. Shell designed the steel tank for holding the LNG, and they did it to kind of like 1940s specs, only they built this in like the 1970s or 80s, and it was a brittle fracture. We knew a lot about brittle fracture, but they were using a 1940s API spec to build it, and it had tremendous welding defects, lousy steel, everything built to a British standard, and they blew up the harbor and killed a lot of people. You can't find out a lot about this but anyway, Qatar took Shell to the World Court over this, and the Shell won because their argument was the Emir of Qatar had a lot of enemies. It was really an RPG hit that was fired at the tank by one of his enemies that blew up the tank. Had nothing to do with the lousy steel and the welding defects and everything else. I didn't work on it. Professor Palou, who's retired from MIT, actually worked on that and told me some of the story. But it turns out for several decades, Shell was no longer welcome to do business in Qatar. Okay, although I have heard that Shell is back into Qatar. In any case, when they actually got and did the dry docking survey, which was in November, the other one was in October, they basically, in Davao City is just a little nowhere harbor in the Philippines. I don't know exactly where it is. I've never looked it up. But they towed it there, and then another one of the empty ships, the sister ships coming back from Japan that was empty, came, and they actually transported over a 3-day period all the LNG from one vessel to the other, so they could unload this vessel and take it to Singapore to get it fixed. Okay, and they were flying pipes and tubing around the world in Learjets just to get all the parts there, and it was sort of an exciting thing to make this transfer in a harbor in the Philippines. But if they had blown it up, I guess they would have killed a few monkeys and other things, but there wasn't a lot of other stuff there. But it was successful, and they transferred the product. Anyway, so she lay afloat in dry dock at this shipyard on 28th day of October, and he looked at the propeller shaft, and he found, is it on this page or the next page? Oh, the tail shaft. On the second page it says, the tail shaft was found sheared in 2 pieces and same was renewed at this time and found satisfactory. By that they meant they put a spare in. They had only 2 spares out of this ship fleet of 6 ships, and they had made 8 ship sets for the propellers. The propellers looked something like this. They had a bearing right here, 6-foot long bearing. They had a 33-inch diameter solid steel shaft, which had broken right here, and they had a couple of other shafts in here. So that's the propulsion system, and the reason it stopped dead in the middle of the Philippine Sea was because the tail shaft broke. So then the question is, why did the tail shaft break? Well, it broke in part because there's a big hole in it. And there's a Singapore shipyard worker. This is a big void. This is a fatigue fracture on the outside. This is a brittle fracture in the center of this thing. And so you got the scale there. What happens is when you make the ingot, because you can't make this by continuous casting, but when they made the ingot, they make it from a killed steel, and the killed steel will have what they call shrinkage porosity, and it will create what they call a pipe, and you're supposed to cut off the top third of the ingot. Now the problem was the shipyard in the steel mill in the United States that bid on this project was in Seattle, and you don't usually think of Seattle as a big steel mill mecca in the United States. And this was a fair-sized steel mill, but it wasn't a really big one. And it turns out, I can't remember how many tons the shaft was, I don't know, 40 or 50 tons. I don't remember. But they had to. This was at the limit of the largest ingot they could cast. And of course, the largest ingot they can cast depends on the crane capacity. Okay, because you got to be able to lift the mold off the ingot, right? Like I showed you before, you got to be able to move the ingots around. You got to be able to forge the whole thing. And you should cut off the top third, but because they were at the maximum size of their ingots, and maybe the ingots, I don't remember, it was 200,000 pound ingot or something like that. It's been 30 years since I worked, 25 years since I worked on this. I don't remember all the numbers, but they couldn't make a bigger ingot. And they had actually had to throw out the first 2 or 3 that they tried to make because they found defects in them after they forged them. And that's sort of what happened here. They were losing their shirts on this job. If you look, this is not forging of this particular ingot, but this just comes out of a steelmaking book. And it shows what happens when you're trying to forge a big piece of steel. These are actually, this is an ingot, this is another ingot that probably has been partially forged, and they forge this much and then they put it back in the furnace. Some of these black spots on here, you may end up with oxide that regrew in the furnace. This furnace will be at around 2200 degrees Fahrenheit. In order to forge the steel, you're going to forge it at around 2000 or above. In order to heat this up, it may take a week in the furnace. Remember, you got this same x squared is proportional to the time. And I told you 10 inches would is about as fast as you can do that, might be 45 minutes. That's with water cooling on the surface. When you're trying to heat it back up and you got something that's 50 inches in diameter, it takes a week to get the heat in, to get it up to temperature and uniform in temperature. During that time, you may form 1 inch thick oxide on the surface. Okay, and when you forge it, all that oxide was brittle and it will fall off. I remember the first time I ever went through the forge at Bethlehem Steel, they had just finished forging and putting some stuff in, and then 2 guys, it was in July, it was hot, and 2 guys bare-chested went in there with shovels and started shoveling the slag off the floor where they just done the forging and throwing it in a dumpster. And they were just throwing it this hot slag at probably that point, it was probably only 1000 degrees, right? It's glowing slightly red. Just throwing it over their shoulder. And as one guy would go down, the other one would come up. And they just were like two cylinders in a 2-cylinder engine kind of going up and down in perfect tandem. And one of them, of course, was throwing over the other guy's shoulder, okay, because the dumpster was over there. And I looked at that as I was just a 24-year-old kid or 25-year-old kid or whatever. I looked at that and said, how can they do that? I said, well, the guy says they've been doing it for 30 years so that they learn to get in sync. And if you didn't learn to get in sync, you get a face full of 1000-degree slag, right? So there's incentive to learn how to do it, right? And never make a mistake, right? But anyway, so when they went to forge it, the problem was they hadn't cut off enough of the end, and they, just to give you another idea of, this is just another thing, this is just a big chain link, okay? And here's a man standing here, and this is the thing that holds it when it's about to go into the forging press to break down that ingot, turn it into some sort of shaft or something, okay? This is actually the same thing. Going into the furnace, this is the forging press. So you guys saw forging downstairs just like this, right? Anyway, this is the other end of the shaft in Singapore, some hard hats there. And here is the pipe. This is the shrinkage pipe. They didn't cut off enough of the top of the ingot because they really didn't have the ingot size capacity in this mill to make this product. But they wanted to get the business, they bid on it, they thought they could do it. The first 2 or 3 they had to scrap because they found defects when they forged them. And they were losing their shirts because they had already scrapped 3 of them. Well, what happened is the technician, the the lab guy, went out with his ultrasonics. He does a inspection on the end with his ultrasonics, and he sees this football-sized hole in the middle of the shaft on his ultrasonics. And he does exactly what he's supposed to do. He goes into his supervisor. He said, I found a defect in this shaft, and his supervisor throws him out of his office. He says, I don't want to hear about it, because the supervisor was getting pressure from his boss because they had already had to scrap the first couple. So what does the guy do? He goes back, he writes it up, he shows he has a little drawing, he shows the little circle on his ultrasonic indicator. He shows it's 12 inches in diameter. The indication that he found with his ultrasonics was 12 inches in diameter. He shows this little circle there. He puts it in the file. They ship it to Quincy, Massachusetts. Back then, people were learning to rely on your supplier for quality control, so they didn't do any incoming inspection at Quincy. Put the shaft in. It worked for 3 or 4 years until the fatigue crack grew and it broke in two. Okay, so they actually did. Quality control works, but you have to have people who are willing to accept the consequences of the results. Okay, and they weren't in that case. And so it ended up costing a little bit more money when the failure occurred in the field. Now, what was the rest of that story that I was going to tell you? Anyway, that's maybe. I was going to tell you about the clink. How this defect was a two-part defect. This is, so they sent me to Singapore. I go out there in a dirty old lay-down yard, and I take this picture. As it's sitting there, they had excised the piece. You had the fatigue fracture up here. You have this brittle fracture around here. And they had excised the piece just for mechanical property tests and things on this steel in the shaft. And they did it right at the interface between the fatigue crack and the brittle fracture. Now the question, and here's your cavity, which was because the ingot had this shrinkage porosity. Okay, why did this occur? Why did the brittle fracture occur? Well, this is what's called a clink defect. And I will tell you that in the last 25 years, not that I talk about this every day, but when I meet other metallurgists, and this could be a couple of dozen metallurgists I've talked to in the past 25 years, and ask them if they know what a clink is, I've only found one metallurgist who knew what a clink was. Okay, I didn't know what it was. Professor Palou, who did the Qatar thing, didn't know what it was. I was only 35 years old when I saw this for the first time. But a clink occurs, so they hadn't necessarily machined it like this, but they had this big ingot had a hole right here. And if you stick if it had been cold, you let the whole thing cool down to room temperature, you get brittle fractures in steel around room temperature. And if you put this in a hot furnace at, let's say, 2,000 degrees, or actually 2,400 degrees Fahrenheit, what will happen? If it takes, before you forge it, it might have to go into the furnace for a whole week. Well, the inside doesn't heat up right away, does it? But the outside starts to heat up, and the outside, as it expands, goes into a compressive stress state. If the outside's in compression because it's heating up, this is hot. If I'm plotting the temperature gradient across here, so if I'm plotting temperature, it's looking like this, right? High temperature on the surface, still cold in the inside. What happens as you heat it up, and this goes into compression, what happens to the inside? It goes into tension. You have to balance your forces, right? So I have a tensile stress state here with a defect right here. So I got tension on this defect caused by compression thermal stresses. This is still at room temperature. This steel has not been worked. It doesn't have fine grain size. It's still fairly brittle even at room temperature. And they call it a clink because You can hear, it's like a rifle shot, clink, when the brittle crack forms, okay? And so in the old Ford shops in the 1920s and 30s, they called them clinks. It's an internal flaw. So when it got to the shipyard, it wasn't just this big thing. It actually had a crack. If you want, I'll make it a V-shaped crack. Had a V-shaped crack. Oops, the V-shape should go that way, right? Running from it all the way up to where the fatigue was. When they put it in service, the only solid metal was that fatigue area right there. That crack was already there, and it formed in the steel mill. When the guy on his ultrasonics, he probably saw something here, but this was so thin when he's shooting from the far end that he didn't really see the crack. He only saw the big void. He probably didn't have it. He should have been able to see it if he wanted to. He could have turned his sensitivity up and he might have seen that crack. But his boss didn't even want to hear about the football-sized void, so why bother to do any finer searching?
Brittle cracking only happens when there's a void there, or does it happen in other?
It can happen other times. It's easier because the void creates the stress concentration, okay? So you get clinks when you have a stress concentration, and in fact what they do to avoid clinking is when you first put it in a furnace, you put it in a first furnace that may be at 1100 degrees Fahrenheit, and that you put it in that furnace for 2 or 3 days until the inside starts to warm up above the ductile brittle transition temperature, so that when you put it in the hot furnace, the steel is not brittle. But the steel, when they first put it in a big furnace like this, was brittle. They may have actually done this. We never got into this type of detail from the steel mill. But because of the void, there was a problem. So the reason I'm telling you this, a number of times in the last 30 years, people, when you're dealing with really heavy section stuff, and not even such heavy section stuff, you'll often see in the specification it says you want to heat up to something to 2000 degrees, and it will say first heat it up to 800, 900, 1100, and then hold it for so many hours, and then heat it up all the rest of the way. This is the reason. And they learned this back in the 30s and 40s, but by the time we saw this in '85, it was an old metallurgist in Britain, Pat Smedley, who knew about clinks. Reggie Pellew, who had studied in the 50s, he didn't learn about clinks. That was old ancient technology. People had solved that problem years before. The problem is, as George Santayana, who was a philosopher at Harvard, said, those who cannot remember the past are condemned to repeat it. Okay? So they ran into a clink problem, and it all had to do with they tried to heat the thing too fast, set up bigger stresses. They had a flaw here, and whether they did a two-step heat treatment or not, they ended up getting a crack, a clink. And frankly, if they hadn't had this fracture, that football shape never would have been a problem, because those of you who are submariners, you know you use tubular shafts anyway because you want to get the weight out, and it's only the outside surface of that shaft that's got the big moment of inertia, right? Right. So you actually drill the center out. So that football hole was not the reason for the fatigue crack here. It was because we actually had a crack here of about 2 feet in diameter on a 33-inch diameter shaft. Okay. Yeah. There's a question back over there. Oh, okay.
So that clink?
Yep.
You know, you drive your car real hard and shut it off through that ticking sound. Is that
Yep.
the same thing going on?
No. This is all thermal stresses, unless something in your car is getting up to a couple thousand degrees. I suspect you have a bearing problem if you're hearing clink clink.
I'm not hearing.
Yeah. Okay. But no, it's probably a different. You may hear a clink, but it's a different clink. Now, I was actually down in a shop, a metallurgical shop in Dallas, Texas once, and they had this shaft about this big. It wasn't 33 inches, maybe been 24 inches. And I looked at it. They didn't have a big football in the middle, but it was a brittle fracture followed by a fatigue fracture on the outside. And so I asked the owner, the metallurgist who ran that shop, I said, that's an interesting fracture you got out there in the back. It was just laying there. We were there for some aircraft part or something. to look at. And he said, yeah, we haven't been able to figure out what did that. I said, what did it come off of? He says, that was one of the shafts for a turbine for a big windmill. You know, all the big, they generate electricity off the big windmills and stuff. And they have big shafts, okay? And this particular shaft, I said, well, I know what that is. That's a clink. Okay, so this was probably 10 years ago that I saw my second clink. I've only seen 2 clinks in my life. First of all, you're not going to see them on little shafts. You're going to see them on really big shafts. And if you think about it, we don't do as many really big shafts as we used to do. And the forging shops that do these things don't exist like they used to. Okay? In fact, that was actually one of the projects I had when I was at the steel mill. They asked me if we could weld together 2 40-inch diameter cylinders, basically 2 ingots or 2 forgings. And the reason was the world's largest single part made out of metal is a 750,000 pound, so 375 ton generator rotor shaft. And this is for like a 1,000 megawatt electric generator. So this is a General Electric or Siemens, Westinghouse. These are the largest electrical generators made in the world. And they're only about, outside of maybe the Soviet Union, I'm sure could do this if they could make decent quality steel. There's one facility, Creusot-Loire in France. There may be one facility in Japan, maybe let's see, who would it be? Tokyo Steel? Anyway, I can't remember the name of the big steel company that does the big forgings over there in Japan. And there were 2 in the United States. One was the Bethlehem Steel Plant in Bethlehem, Pennsylvania, and the other was U.S. Steel. And those facilities back in 1975 would have cost $2 billion to build a new facility. And so they didn't want to spend that kind of money. You could buy half of a steel plant for that back then. Now to build a facility like that might be $10 or $15 billion. And that's the whole facility to forge the shaft. This is not the steel making part. This is just forging it, machining it, heat treating it, all these other things. And the only reason, and you have to, in the heat treatment, you can't just kind of stick these things in a furnace to do the heat treatment and lay them horizontally. You actually have to do it vertically. And this shaft might be 40 or 50 feet long, so you got to have a 40-foot furnace. Typically it's buried in the ground, goes about 4 stories down into the ground. And the reason we had the one at US Steel and Bethlehem Steel is because they've been put in at the beginning of the 20th century to make battleship gun barrels. Okay, and remember they used to always want to have 2 facilities. Actually, you guys don't remember that. But back even 25 years ago, that was one of the big things. They always wanted to have 2 shipyards. Actually, you still have 2 shipyards for subs, right? But that's actually one of the only legacies that still has that. You don't have 2 shipyards for carriers or anything like that. But the subs are more conservative than the carriers. But in any case, Bethlehem Steel and US Steel, the facilities had been put in like 1910, 1915 and stuff to make battleship gun barrels. But now they were the only 2 places outside of Japan and France that could make these huge generator rotor forgings. And at the time, the growth in electricity demand was such that the world was not going to have enough capacity, because you could only make, I can't remember, it was something like a half a dozen or a dozen of these things a year. Okay, it would, you know, because it takes 2 weeks in the furnace to warm it up, right? So you start figuring this out, and you may have multiple furnaces for forging and for heat treatment and stuff. But just to put one through the whole process might take more than a year. You might have a dozen of them in production, but they're at different stages of production, and there was no way, based on heat transfer, to get more production. So they wanted to know if they could make smaller ones and then weld them together and make big forgings. And so I had to figure out could we weld 40-inch thick steel shafts together? So. Well, we never did it. No one wanted to spend the money to actually do the trial, okay? Yeah, you could have used electroslag, you could have used narrow gap welding. There were a couple of welding techniques that could have done it. And actually every now and then people run into these things. It's about 20 years ago, the guys over here at the MIT Plasma Fusion Center came to me and they wanted to weld 20-inch thick by about 4-foot long stainless steel together. And this was going to be for the top dome of the International Thermonuclear Reactor that they're building in France now. But they had to, I mean, there was no place they could forge something this big and in stainless steel, so they wanted to know, or actually if there was, it was going to be too expensive, and they wanted to know if they could weld a bunch of smaller pieces of steel together. So every now and then someone wants to weld a piece of something that's 20 inches thick. Can it be done? Yes, but you know, you can't spend a lot of money on procedure qualification when you can't make a lot of test welds and have them screw up. Just to show you the microstructure in the Libra steel, it had not only a brittle steel, but it had, the microstructure was fine from the heat treatment and everything, but it had small cracks. It had porosity and cracks that had formed during the brittle fracture, and cracks growing from those defects. So that was the cause of the Libra failure. It's kind of an interesting story in casting technology, the pipe. A shop that bid on a project that was a little too big for them, and an inspection procedure which caught the defect but didn't get past the managers who were afraid of losing money. So that's that case study.
When it was found that that was faulty, it was deliberately sent out, even against the objection of the fuel action.
Yes, that was why I was involved. The legal action was such that it was clear the steel mill was guilty of making something bad. But and I don't remember all the political reasons, the ship owners, who were based in, the company was based in New York, basically wasn't getting along with General Dynamics, the shipbuilder. This is the commercial shipbuilder down here in Quincy. But General Dynamics owned that yard. Originally that yard was owned by Bethlehem Steel. They had built it for World War II, I think, I don't know. They built a lot of Liberty ships down there, okay? But Bethlehem Steel had sold it to General Dynamics, and they had a number of problems. This was a really high technology ship to build these LNG tankers. They were some of the first really big LNG tankers in the world, and they had a number of problems with them. And so the shipbuilder there was a lot of bad blood between the shipyard and the owner. And so the owner decided to get together with the steel mill, and the two of them legally going against the shipyard. And it was like a $15 million loss, and I think the shipyard ended up paying 6 or 7 or 8 million. Even though their problem was they didn't do incoming quality inspection, okay? But it was really bad blood between the shipyard and the owner, okay? However, and I always felt that the steel mill in Seattle had really gotten away with murder. Not murder, well, no one got killed. However, I'm going to turn the tape off for just a second.